Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today, I have managed to complete day 20 of the advent of code in Rust. This was particularly satisfying after day 19, which if you didn't see, I'll link at the top and in the description, where I ended up giving up and having to steal 2 solutions and get 1 hint to even complete the puzzle. So day 20, being able to do it on my own without any help was actually quite reassuring. So let me read the puzzle out to you, and then I'll take you through my solution for part 1. Then I'll read part 2 and take you through my solution for part 2. So, day 20, race condition. The historians are quite pixelated again. This time, a massive black building looms over you. You're right outside the CPU. While the historians get to work, a nearby program sees that you're idle and challenges you to a race. Apparently, you've arrived just in time for the frequently held Race Condition Festival. The race takes place on a particularly long and twisting code path. Programs compete to see who can finish in the fewest picoseconds. The winner even gets their very own mutex. They hand you a map of the racetrack, your puzzle input. For example, you can see here we've got the maze with the start and the endpoints. The map consists of track, which is a dot, including the start, S, and end E positions, both of which also count as track, and walls, which is a hash. When a program runs through the racetrack, it starts at the start position. Then it is allowed to move up, down, left, or right. Each such move takes 1 picosecond. The goal is to reach the end position as quickly as possible. In this example racetrack, the fastest time is 84 picoseconds. Because there is only a single path from the start to the end, and the programs all go the same speed, the races used to be pretty boring. To make things more interesting, they introduced a new rule to the races. Programs are allowed to cheat. The rules for cheating are very strict. Exactly once during a race, a program may disable collision for up to 2 picoseconds. This allows the program to pass through walls as if they were regular track. At the end of the cheat, the program must be back on normal track again, otherwise it will receive a segmentation fault and get disqualified. So, a program could complete the course in 72 picoseconds, saving 12 picoseconds, by cheating for the 2 moves marked 1 and 2. Or a program could complete the course in 64 picoseconds, saving 20 picoseconds, by cheating for the 2 moves marked 1 and 2. Down here. This cheat saves 38 picoseconds here, and this cheat saves 64 picoseconds and takes the program directly to the end, 1 and 2. Each cheat has a distinct start position, the position where the cheat is activated just before the first move that is allowed to go through walls, and end position. Cheats are uniquely identified by their start position and end position. In this example, the total number of cheats, grouped by the amount of time they save, are as follows. There are 14 cheats that save 2 picoseconds, and so on, down to 1 cheat that saves 64 picoseconds. You aren't sure what the conditions of the racetrack will be like, so to give yourself as many options as possible, you'll need a list of the best cheats. How many cheats would save you at least 100 picoseconds? You can see here that I got the puzzle answer of 1332. Okay, so one quick point to note that you may not have understood very well from the reading out of the puzzle, because a lot of people online seem to struggle with it, is the fact that you can turn off collision for 2 picoseconds. People are getting confused and thinking that that would allow you to move through 2 wall segments because your collision is disabled for 2 picoseconds. But no, you can only skip through 1 wall segment. That's because, let's say you're at the start position here, you activate your cheat, then you move 1 picosecond into the wall and 1 picosecond back out again. So in 2 picoseconds, you have to be back on the track, which means there's only 1 wall segment that you can skip. This understanding this comes in useful for part 2 as well, but we'll get to that. So let's switch to the code and I'll explain my process of solving this one. Okay, here we are in the main file. Now I am again using the pathfinding library, particularly the grid class and the Dijkstra algorithm in order to solve it. So I have my race maze, which has a grid which contains the walls and the track, the start position where I start, and the end position where I should end. Now, I do have 2 unit tests, no more than that. One test part A, the right solution, which is 4, according to the puzzle. Right, so because the example gives the list of possible solutions, it doesn't actually give you one single answer. So here I'm setting a threshold of 36 picoseconds. It needs to be at least 36 picoseconds, of which you can see there are 4 lines, each containing 1 cheat. So I've taken from this example one particular case, a threshold of 36, where the result is 4. Okay, so that's the test case. That's what I started working with. Next step was to parse the puzzle. And similarly to day 18, I believe it was, I used the grid class, and again, I parsed the puzzle and checked that it had a start and an end. I think that's all I was checking. So this maze error enum has 4 enums that I use while actually parsing the puzzle, and one that's used while trying to navigate the puzzle. So it checks for, it goes through all the lines. I've constructed it so that it doesn't store the walls. So it will skip the line here and here, and I'm doing a thing which may not be true, which is that if it doesn't have a dot in, then I'm skipping it. And I think that's reasonable because if it's a complete wall, then I don't want to have it. However, if I did manage to get a wall in the middle of the puzzle, then it's not solvable. So I am guaranteed that there will be a path through the maze, right? So I can skip any lines in this puzzle that are completely filled with hashes or don't contain any dots, right? So that's not always true, but in this case, it did work. So then I went on to each row, checked whether it was a track space, a start or an end, and saved those, and a hash for it to be a wall, which I just didn't add to the grid, so that the grid knows it's an invalid position. Then I check whether the start exists and whether the end exists, and then I construct the grid from the coordinates. From there, I have a race maze that I can use to solve. Then I went on to implementation. Now, my first attempt at solving this was, it was fairly naive. Essentially, I went through all of the non-track cells in the grid, and I turned them to cells, and then I did a new pathfinding algorithm to see what the new shortest path is. So that looks like getting the base. You only need the base time. The base path comes from an optimization, which I'll come to. So the base time does a Dijkstra solve from the start point to the end point. For each point, it gets the neighbors from the grid of that vertex, and then it applies a cost of 1 to each of those neighbors. So that's the puzzle solve. That gives us the base time, which from the puzzle is 84 picoseconds, I think. Then I went on to create an inverted grid. Now, the point of this was that I wanted to find all of the walls. So to do that, I could either, I needed to use the grid iter function in order to find the valid cells, but I wanted to be able to find the walls. So I created a copy of the grid where I inverted it so that the walls become the valid positions and the valid positions become the walls. From there, I'm able to iterate over the grid and find all the points where the walls are. This is actually from the optimization. So you can ignore this block of text. This was me thinking about how to do it in a better way. So my algorithm was originally something like for index point in grid or inverted dot iter dot enumerate, and then I could self.grid dot insert or add vertex. There it is. It would be the point. Then I can do the solve. and then I can remove the vertex again. And if I want this to be an immutable method, which I do, then I can just take a clone of it. So it'd just be self.grid.clone, and then use grid.addVertex and grid.removeVertex. So I can do the solve exactly the same way, right? I'm just using this Dijkstra function call, except that instead of using self.grid, I'm now using my altered grid. So instead of self.grid, it is just grid. So that gave me the new shortest path through the maze. And from there, I ran just some very easy maths. Basically, there's a hash map for time saved. So for every time I save a time of 20 picoseconds, it will have an entry in that hash map with a count of 1. And then if I get another point where 20 picoseconds is saved, I can add 1 to that. So here we go. If let sum is Dijkstra, grid.neighbors, etc. Let time saved is the base time that I found. That's the shortest path without cheating. Minus the time that I just calculated from this. So we're trying to find the time saved, remember. Minus the index. Now the index is because it's part of the optimization. So let me now take you through the optimization of it. Originally, I went through all of the walls in the entire puzzle and checked removing all of them. And I realized that, let's take a look at a valid path. Okay, let's just take an example of this point over... I don't know if they're all valid in some way. I think they might all save it. Okay, so this point here, right? This is a wall that's in the middle of a bunch of other walls. There's no point checking this wall. So instead of iterating over all of them, I needed to find the walls that were relevant to the puzzle. And those are the walls that are beside the base path. So the shortest path, there's only any point in removing walls that are adjacent to that path. So that was the optimization. What I did was I kept the base path from my Dijkstra algorithm. And then I kept the inverted grid, but I also added my vertices from the base path. And that is so that I can use it to find the walls that are neighboring the base path. So if I didn't do this step, then when I say, give me the neighbors of this point on the base path, it would say that vertex doesn't exist in the grid, therefore it has no neighbors. But I needed it to give me the walls that neighbored it, but not the valid points. So I added the entire base path into the inverted grid. Then, for every point in the base path, I keep the index and I keep the point I'm checking. Then I get the cheat candidate from the neighbors of that point. Now, there's no point checking, because I've added all of the base path into the inverted grid, it's going to give me base path values as possible cheat candidates. So I want to immediately remove those. If the base path contains the cheat candidate, then just continue. There's no point. Also, there's no point in continuing if it's the end. But I think because the end is on the base path, this actually doesn't do anything. Then I add the cheat candidate to the normal grid, the one that correctly has the walls and the points, not the inverted. Then I do the Dijkstra search, and I check the time, save it in, and here's where the minus index comes in, because I'm not searching from the start point. Okay, I'm searching from the current point on the base path. And that's because there's no point searching from the start point when I've already partially solved the path, right? I need the shortest path from the base path with the wall removed, because it wouldn't have done anything earlier along on the path. So there's no point recomputing that. So I search from the current point on the base path to the end. So let's say that I have my wall that I'm testing removing here, right? So the valid path is coming up and around. Now I can cut through. So there is no point calculating the base path for this entire region, because it won't have changed from the cheat candidate that I've just used. So from this point to the end, that's what I calculate, and that's why I have the minus index, because I'm partially along the base path and I need that time added on for it to be correct. So up to this point, I may have traveled 40 picoseconds. Then I calculate how long this path is, which is, say, 7 picoseconds. So my total travel time is 47 picoseconds, for example. From there, I have my time saved hash map, and I'm just going to go over it and check if it's greater than the threshold. I pass the threshold in as an argument, even though the puzzle gives it hard-coded, because the test text and the input text have different thresholds that I'm checking for. The real puzzle wants a threshold of 100, but the test text doesn't save any entries of 100 picoseconds or more. So I coded the threshold in so that I could use the same function to solve both cases. Now this works. Unfortunately, it works fairly slowly. So let me show you it working. I'm going to remove this, and I'm going to reinsert this, and then I'll run it in release mode so that you can see the time. Now I won't speed this up or cut through it. Yeah, I don't need this anymore. I think I can get rid of all of this as well. Let's try that again. Okay, so it's taking some time and it's still going, and that's because the input text is a very large maze, and it's repeatedly doing a Dijkstra solve through it. So even with speeding it up, only calculating from partially along the grid, it still takes quite a long time to run. It solves in reasonable time, and I do get the correct answer, but I knew from this algorithm that I needed to do something differently. There we go, OK 1332. So I entered this into my answer. Now, I'm going to read through part 2, because it's actually part 2 that helped me realize how to optimize part 1 better. Let's go to the puzzle, and we're going to read through part 2. The program seemed perplexed by your list of cheats. Apparently, the 2 picosecond cheating rules deprecated several milliseconds ago. The latest version of the cheating rule permits a single cheat that instead lasts at most 20 picoseconds. Now, in addition to all the cheats that were possible in just 2 picoseconds, many more cheats are possible. This 6 picosecond cheat saves 76 picoseconds. Because this cheat has the same start and end positions as the one above, it's the same cheat, even though the path taken during the cheat is different. Cheats don't need to use all 20 picoseconds. Cheats can last any amount of time, up to and including 20 picoseconds, but can still only end when the program is on normal track. Any cheat time not used is lost. It can't be saved for another cheat later. You'll still need a list of the best cheats, but now there are even more to choose between. Here are the quantities of cheats in this example that save 50 picoseconds or more. Here's the list. Find the best cheats using the updated cheating rules. How many cheats would save you at least 100 picoseconds? Okay, so a note here, as I was talking through part 1, I said it's useful to understand the number of picoseconds. So the problem here is that 20 picoseconds are possible, right? That means you can skip 19. And they don't need to all be wall. They can be track or wall. You just want to stay with your collision off for that entire time. So with that in mind, we can't skip 20 segments. We need to end on a valid track position. So let's go back to my revised part 1 solution, which was much faster. And then I'll talk you through the part 2 solution, which is very similar to my part 1 solution. Okay, here's my part A alt function. And again, I pass it in a threshold. And for both of these, by the way, I'm returning a result of usize and race maze error. And that's because if there's no path available, I want to be able to return that possibility. It means that I can use question marks to unpack results, which is nice. Rust forces you to do the right thing because it's the easier thing to do. It makes the wrong thing too difficult. Okay, so here is the core of the new algorithm. It's Dijkstra Reach. What this function does is that from a particular point, it calculates all of the points on a grid that are reachable, or on a graph rather. And it keeps the shortest cost to each of those paths. So I am essentially doing a whole bunch of Dijkstra pathfinding algorithms, except in one go, so that it's all kept, the results are all kept, the algorithm doesn't need to recompute from scratch every single time. By doing this, what I'm doing is finding the shortest path from a particular point. So if I manage to cheat through a wall into a new point, I already know the shortest distance from that point to the end. I've essentially shortcut this Dijkstra algorithm because I've got it stored in a data structure. I can just look it up. No need to redo the Dijkstra. And that's the core of the optimization. I do one Dijkstra each, and then I find the base path and the base time in the same way. I still need to do this, I found, because I wanted the path, right? I only want to check walls that are beside the path. So I did a fresh Dijkstra. Now, funnily enough, now I think about it, there's probably not that many walls that are irrelevant. So I probably could have just checked all the walls instead of just the walls along the base path. And that probably would have been quicker than doing another Dijkstra search. So premature optimization there maybe, but I was copying it from a previous function and it was easier to leave it in than to rewrite the code. Call it quicker in coding time than in execution time maybe. So then I still have my inverted grid, but I have a new grid, the filled grid. So what I'm doing with this is that because while my collision is disabled, I can pass through valid points just as well as I can pass through walls. I can't use inverted to get my neighbors anymore. I need to have all the possible points within that size of grid. So that's why I'm doing that. Now I can do a neighbor search from the filled grid. So I keep my hash map of time saved. I'm iterating along my base path. And now my cheat candidates is whether the I get all the neighbors of the cell along the base path from inverted. And that's, so part 2 is when I need to think about the track being able to pass through. So here, cheat candidates is inverted, and I get the neighbors of the cell. I check whether they're on the base path. If they're not on the base path, then I keep going. Otherwise, I filter them out. And then I copy it so that I have access to the raw usizes. Then I create a second hash set. I don't need to do this, by the way. I could probably have just carried on from the filter to the flat map. But I separated it out so that you can see what my logic is. And so I could keep track of it myself. So for the endpoints, I go through all of the cheat candidates. These are hash sets, by the way, to deduplicate the endpoints for a particular point. And then I get the neighbors for that vertex, which provides a list of neighbors. So here I'm using a flat map, because if I used a map, then I would have a list of points. I don't want that, I just want one long list. So I use a flat map, which takes a vector of vectors and it flattens it out. So it spreads them all out, so it's one long vector. By doing that, I group all the neighbors together. Again, I have another filter. I need to check that the cheat candidate I'm checking is not the cell that I'm currently on. And I want to check that the vertex, the endpoint is actually a track point, right, in the real grid. So what I've kind of glanced over here is how this works. How this is working is, for a point along the base path, I get all the neighbors that are walls. And then for all of those walls, I get all the neighbors that are valid track. So that means that I can go 1, 2 onto valid track. So that's a valid cheat. As part of that, I also get what the endpoint is. So I don't need to store the wall here. I only need to store the endpoint that I know I can get to by cheating through a wall. So then I have a list of valid endpoints that are on my real grid that I know I can cheat to get to with one cheat that lasts 2 picoseconds. Then I go through all of those endpoints and look them up from my reachable list, which I defined at the start here. So from that, I find the node where node.node is the endpoint, meaning I look up from reachable my particular endpoint, which gives me a Dijkstra reachable item. Then I can get the time taken as the total cost of that point, and I can add it onto the index, because remember, I'm somewhere along the base path here. And then my time saved is the base time of so the fastest time with no cheating, dot saturating sub time taken. So what that does is, because I'm dealing with unsized numbers, a saturating sub will subtract, but it will stop at 0. So I won't ever get a negative number by doing a saturating sub. So if the time taken has somehow gotten longer by doing this cheat, then I will just have a 0 time saved rather than a negative time saved. Then I just look up the entry in my time saved and add 1 to it. I do exactly the same algorithm with the cheat saving threshold and give the answer back from summing across those filtered points. So that's it. That's my actual finished part 1 solution. And I can show you the two in order. So if I go to main.rs, I'm going to run this. So you'll see, again, the time that it takes for the part A unoptimized version, and then you'll see the optimized version where I just do 1 Dijkstra each to find all the possible paths and then figure out how to hop onto them. And you can see that popped up immediately. Now, there was a problem here, and I left it in, is that I'm getting the wrong answer. And the reason for that is that I haven't considered the time taken while cheating. So my time taken here, I think this is the right function. Oh no, this is part B. My time taken here I've labeled as the index, how far along the base path I am, plus the total cost from the cheat endpoint, right? The endpoint that I'm checking to the end. There's actually a 2 picosecond gap in there that I've neglected to include. So I would actually take 2 more picoseconds. So I should actually write +2. Now I'm going to undo this and I'll rerun it. And this gives me the correct result, 1332. And that's important because when I did part B, I needed to account for that root time because it's up to 20 picoseconds you're cheating. So it can be less than 20 picoseconds, so I have to include that calculation. So now that I've explained that, part B will actually be very quick to explain because it is essentially the same algorithm, except that it's a different way of calculating the cheat candidates. So for part B, I find the Dijkstra reach exactly the same. I find the base path exactly the same. I keep my time saved. Now you'll notice here that I don't have an inverted grid or a filled grid. I don't need either of them for this. How I'm finding my cheat candidate is that I iterate over my grid, and for any point, I find the distance is less than or equal to 20. And the reason, and I could have done this in the previous example as well, I could have checked whether it's less than or equal to 2. This, by the way, I've relabeled this to dist threshold. So I pass in a distance threshold and a time threshold. I didn't need to. The distance threshold is the same in both cases. I just felt it was neater to do that, so it was obvious. So here, instead of doing a neighbor and then another neighbor's, or even doing that up to 20 times, which is my original plan, I simply take all of the cells in the grid. Now, I started out by doing this using the filled grid, so that it would give me wall endpoints, and then I would filter out the walls to see if it was a valid endpoint. And then I realized there's no point. If I just use self.grid, I'm trying to find the endpoints that it is allowed to cheat to. I don't need to check the walls. I can just check that the endpoint is valid and check that the Manhattan distance is less than or equal to 20. So that's all I do. It's filter with grid.distance, which is the Manhattan distance, and check that it's less than the threshold. From then on, it's exactly the same. I check whether it's in my reachable list, I find the time taken, and here is where I do the path length, by the way. I can check the distance from the cell in the base path that I'm cheating from to the endpoint that I'm cheating to. And I can tell what the Manhattan distance of that is, and that is the length of the cheat. Then I can get my time saved from that with a saturating sub, add it to my time saved, and sum across all the time saved that are over the time threshold. And that's it. So I can reinsert my part B. Here we have a distance threshold of 20. We're allowed up to 20 picoseconds of cheating, and 100, where we want to see all the cheats that save 100 picoseconds or more. Let's run this for the final time. Part A is complete. Part B takes a little more thinking time. And there it is. That's the final result. Now, it did take a few seconds to calculate part B, but I can't think of how to optimize it anymore. I am satisfied with this solution. I really enjoyed the puzzle. I found that having the reachable was a really nice optimization that really sped it up. I was really pleased when I found that. So with that, that is day 20 complete. I'll see you again tomorrow for day 21. Or next video, we'll see how difficult day 21 is. And thank you for watching. I'll see you then.